Let me introduce our speaker today is Akhil Uniyal. He's a PhD student at Shanghai Jiao Tong University. Started to do this PhD in 2023. And prior to that, he graduated from the University of Delhi in 2018 and then was a junior research fellow at the Guwahati Institute of Technology in Assam, India. And now he's about to finish the PhD thesis and applying for postdoctoral positions. So that's how we got to know each other. So welcome, Akhil, and please tell us about your research.
Hi, hello everyone. Thank you for the invitation. Maybe I can share. So, thank you. So I'm a PhD student at TDLI. So today I will be presenting my recent work, which has been published in Nature Astronomy. And in this work, we try to. So this work is in collaboration with Luciano, Yusuke, and a postdoc Indu. Yusuke is my supervisor here. So let me start with the background. And so what we want to do is we want to take advantage of EST observation of M87 and Sagittarius A star. And why this is important to test gravity with this observation, which we can understand from this right-hand side plot. So here in the x-axis, you have a gravitational potential, and in the y-axis, you have a curvature. And all of the observation that we have done in different scales can be put into this parameter space. And particularly for EST observations of Sagittarius A star and M87 is at this regime where you have very high gravitational potential, as well as your curvature is very high, close to these black holes. Now, similar thing we can also see. For the neutron star cases where you have high curvature. But why the M87 and Sagittarius A black hole are important to easily test the GR theories. So which we can understand from this left-hand side plot. So as we can understand that all of these observations can be categorized in 4 different ways. And some of these observations are very sensitive to the dynamics and propagating mode of this propagating mode of the gravitational field, like gravitational waves, pulsar orbits, and the cosmological test. And on the other hand, the observation like black hole shadow is only sensitive to the stationary metric information. Similarly, some of the observation are very sensitive to the coupling of the matter field with the gravitational field, like neutron star observation. And the black hole shadow is only important if you know the properties of the vacuum field, vacuum space-time. So as you can see, the black hole shadow is only sensitive to the stationary matrices and vacuum solution of your Einstein theory or any other gravitational theory. And we don't need to care about much dynamics and matter around it. And that's why this is much more easier to test gravity theories, and we want to understand whether the future observation have the capabilities or not, and also what is happening with the current EST observations. Apart from that, there are a few questions that we also want to answer in this project, which is also we have within EST as well, and we're trying to understand these such questions. So one of the main important question is about the variability of the Sagittarius A star. So the observation that we have done for Sagittarius A star has this huge problem compared to the GRMHD models that we have performed with the Kerr solution and the plasma physics. The variability of the GRMHD model is in the light curve is too high compared to the observations. And this is a big puzzle for Sagittarius A star observation that we still try to understand. Another question is what happens to the jet? So because we don't have any jet for Sagittarius A star, so we want to understand what happens what happens to the jet when we go to the alternative space-time or away from the Kerr solution. Another question that we try to understand is what happens what the compact object that we are looking at, whether it is a black hole or it is a mimicker of a black hole. And of course, then there is a plasma effects, and we want to understand how these plasma effects contained within the black hole shadow images in the Kerr and away from the Kerr black hole. So just to have a physical picture or the general idea, so here I'm showing you which is called a pizza plot in EST papers. You have seen, must have seen it. And so we have two different models like MAD and SANE, magnetically arrested disk, and a standard and normal evolution of the magnetic field. And the only difference is that you have a very strong magnetic field for a MAD case and intermediate magnetic field for the SANE case, where you can actually produce jet. Now, if you go from these two different plots, you are going from very highly spinning, negative highly spinning black hole to non-rotating black hole to highly spinning positive black hole cases. And from left to right, when you go in one plot, the number 1, 10, 40, 160 basically shows you changing the ion to electron temperature ratio. And on the curve, you're basically changing the inclination angle of your of the observer plane. And the red color here shows the GRMHD. So all of these models, GRMHD models, are tested with 11 EST constraint from the Sagittarius A star. And red means all of the constraints have failed, and yellow means some of the constraints have passed. And interestingly, if you remove the variability constraint I have talked about, none of the model are going to pass. All of the GRMSG models are failing. But if you remove the variability constraint, then only two models pass, which is shown by the green color here. And these two green colors shows very high spinning black hole. So which means there should be a jet, but we don't see any jet in the observed frequency of EST. So clearly there is some hidden physics in either in the space-time of this black hole or the plasma physics itself. And here we want to understand whether when we change the space-time, how all of these properties are changing and how they are directly dependent upon the space-time by asking simple question whether the Einstein theory is correct, very close to these black holes or not. So how we do it? So there's a very simple recipe to do it. So first you need to have a initial condition to start your GRMSD simulation. So you must have a consistent initial torus solution, and which you can use for any axisymmetric spacetime to perform the non-Kerr simulations. Once you have the initial condition, you can evolve your GRMSD equations and have the simulation and do the post-processing to produce a black hole shadow image. And then you can, of course, do the theoretical modeling on it and go to the current EST resolution or any resolution that your telescope has. And then you can compare it with the observation image that you have done with your telescopes. And you keep on doing it until you get the best fit. So the first challenge is to have a initial condition for your torus solution. And what we did, what we were more interested in how to get this initial condition more in a consistent way that you can actually compare it with the known Kerr solution that you have. So this paper we published in 2024, where we developed a generalized Fishbone-Moncrief torus solution, and we tested its stability in the hydrodynamical equilibrium regime. And this, so like I'm showing here, this is Kerr and Kerr case when you evolve your hydrodynamical equilibrium torus to a very large time. And you do the similar thing with our own developed torus, which is which is labeled as non-Kerr here. And as we see that it remains in the hydrodynamical equilibrium. And the leakage of matter that you see is basically a perturbation that we introduce here in the pressure to check whether it remains in the equilibrium with the small perturbations or not. And in the right-hand side, we show the similar thing in the in 1D plot with density and pressure for going from the small deviation from Kerr to the larger deviation to the Kerr, and we show that okay, this torus always remain in the equilibrium condition no matter how deviated you are from the Kerr solution. So once we have this initial torus solution, which can be used for any axisymmetric and stationary vacuum space-time, we next thing we need a space-time metric information, which can be used in a generalized form, that you can actually have a sense that you don't want to perform all of the simulation in different black hole solution, but you want to make it more in a more generalized way. So for that, we looked into the something called a parameterized metric known as Konoplya-Rizzola-Zedinsky KRG metric. And in this metric, the interesting thing is that all of the known black hole solution, like any solution that you know, like charged black hole solution or scalar black hole solution, all of these solution can be mapped into this parameterized metric. And how do you do the mapping? You can always use its components like A0, A1, and so on to map all of the exact solution of that black hole into this parameterized metric. And what we wanted to do here is we wanted to take only those components which can affect your GT5 component or your frame dragging or enhance your frame dragging around this black hole. So we found out that only two components of zeroth order and first order correction is important. All other high order correction does not change it much. So we kept two parameters only, A0 and A1, which you can see in the right hand side plot. And these two parameters has extremum limit when both goes to 1. And this red curve here shows a maximum deviation from the curve, which is shown in the black. So now, so we perform these 4 different cases, and the maximum cases goes when both of the parameters are 1 and 1. And now once we have this initial torus solution, which we built, and then you have a KRG metric, which is more generalized metric, you can perform the simulation. So that's what we did. And here I'm showing you a 3D image, 3D plot of this GRMHD simulation. And on the left side, you have Kerr, and the right side, you have extremum limit of this KRG black hole. And first thing that we noticed that as your frame dragging effect, okay, so the constraint that we put here, we fix the horizon for all of these black holes. And we also fix the spin for all of these black hole so that we can, so that any deviation that we see, it's coming from only from the frame dragging effect. And one thing we immediately notice that as your KRG black hole goes to the extreme limit, your magnetic fields get more attached to this black hole, which does reduces or narrow down your jet region. And that you can see from this figure and this figure that the jet region becomes narrower, but the field line gets more concentrated into the black hole. And the jet region is basically the region where you have very high magnetization with sigma is greater than 1. And you can also do the quantitative analysis on this. So here you have a Kerr black hole, here you have a non-Kerr black hole, which is KRG extremum limit. And this black curve that you see is basically sigma is equal to 1 contour, which is shown here for the average images. And as we can see that this red one, where you have extremum limit of this KRG, your jet region becomes very narrow. But if you look at the sigma, it becomes much higher for KRG than KRKs. So this is some dynamical evolution that we have seen here. But what we want to understand how this information goes into the images of this black hole, and whether we can, because from the observation we are going to see images, and how we can see those changes within the images. So what one can do, one can simply do the analytical study. And so this is known as the critical curve, a photon ring for different cases on the observation plane. And the blue one is for the Kerr case, and the red one is for the extremum of the KRG case. So as I said, that your spin of the black hole and the horizon of the black hole is fixed, but because of this frame dragging effect, the photon ring itself get much closer to this black hole, and it goes attached to black hole is more compared to the Kerr black hole that we have seen. Now, the similar thing you can also get from the simulation that we have performed here. So in the left-hand side, you have Kerr here, and this is your extremum KRG case here. And as you go from Kerr to KRG, as the frame dragging effect increases, your photon ring gets more and more closer to this black hole. And the intensity of this photon ring can be understood by if you do a cross-cut profile at y equal to 0, like we did in the right-hand side plot, and the intensity gets higher for the KRG case on the photon ring itself. However, what we want to understand whether, okay, this information, you can understand this information if you have infinite resolution, but you don't actually have infinite resolution. And what we want to understand what happens when you go to the EST resolution, which is 20 microarc second. So we did the theoretical modeling here in the lower panel. And as we can see from Kerr to KRG, first thing is completely lost. You don't know where is your photon ring. Second, the image is so blurred that you cannot get much information from these images about the space-time. So the natural question is, what will happen when the future observation will come up, whether we see any differences or not? And just to give an example, so let's say you have the simulation image here, and you put your blurring from to this image, where the maximum emission is coming from this part, and you put this blurring from 5, 10, and 20. 20 is basically where EST is, and 5 is where your black hole explorer is expected to give you. And as we can immediately see that the photon ring gets much more localized. And if you have more brightness or you go more and more higher frequency, the photon ring will be much more brighter, and you can localize it much more easy way than compared to the current EST observation that we have. But what we wanted to understand is we wanted to perform a more sophisticated study on this. And because if we have this information, whether we can really understand the fact that GR can be tested or not, it can only be done if we do some systematic analysis. And that part we performed here. So so in this plot, what I'm showing in the y-axis is something called normal cross correlation. So what does it mean? It basically compares the two black hole images. So, so when you have a 0, which means two black hole images are very much similar to each other. And its maximum value, it can go to 1, where both images are completely different. And in the x-axis, I have beam size, which is angular resolution of your telescope. As we have showed here, EST and Black Hole Explorer going from 20 to 15 to 6 microarc second. And what the normal cross correlation do is you have two images, and you first get rid of the extended brightness and contrast, and then you compare pixel by pixel both of these images. And the information that you get in this plot is mostly coming from very close to these black hole, and the pattern that your photon ring is showing in the image plane. And then, of course, when the beam size decreases, as the photon rings becomes much more clear, the mismatch or the normal cross correlation becomes higher and higher. And particularly for the Black Hole Explorer case, it can go for the KRG case, it can go till 8%. And just to, as I initially said, that any black hole can be mapped to these KRG parameters. We have shown here one special case, which is dilatant black hole, non-rotating dilatant black hole. And it comes within the shadow region. So basically, you can actually map this black hole into this parameterization, and the black hole itself comes below this shadow region. So this mismatch we wanted to understand whether this mismatch depends upon the plasma physics or not, or whether this is really a space-time property. So for that, what we did, we changed this ion to electron temperature ratio that I have talked about in the PISA plot. We changed it from two different cases, 10, 40, and the earlier one was 160. And this number that for the Black Hole Explorer and GST and EST, this remains very much similar. So the effect is not coming from the plasma physics, but rather coming from the space-time deviation that we have introduced by this parameterized form. And we can perform the same study for different inclination angle, and you get the similar differences for when you compare Kerr with the KRG black hole. Okay. So another thing that one can do is one can always talk about the diameter of the photon ring. what we wanted to show here, how so like I said that, okay, you have this photon ring, and when you do the crosscut, you have two peaks, and the location of these two peaks can be taken as a diameter of this photon ring, and the 99% of this top peak or this top the top peak or the peak of this diameter intensity can be considered as the uncertainty of your observation as well. So that's what we did here. So you have this diameter in the y-axis and the beam size in the x-axis. And as you introduce more and more, as you blur it more and more, your photon ring information goes lost, and you have almost overlapping with the uncertainty. So you don't actually have much information beyond 5 and 6 microarc second about the space-time. And what you can always do, you can calculate a quantity which is the difference of the diameter between Kerr and KRG, and normalize it by their uncertainty. So when it is much greater than 1, you can clearly tell, okay, this is completely different space-time that you're talking about. When it is less than 1, then your uncertainty in your diameter is much higher than the measure of your own diameter. So that's what we showed here, that for the black hole explorer, it's much more easier to have this distinguishability between the space-time by this quantity, where if it can reach much greater than 1. Okay, so just to have a feeling what happens when we go from EST to Black Hole Explorer. So this is your simulation, and this is the current EST resolution. And the future Black Hole Explorer is expected to show you more information about the black hole, about the photon ring. And you can actually then have much more systematic analysis by calculating this image quality metric, NCC, or diameter intensity, which we have shown, to understand whether you are actually looking into the Kerr black hole or it's already beyond Kerr black hole. Okay, so for conclusion, so this is the first time we can understand that we can test theory of gravity very close to this black hole. And we did we took the advantage of this by calculating by performing the 3D GRMHD simulation with the KRG metric and newly built torus solution. And one thing is important, that we did this this analysis for MAT case, but for same case, we expect the similar conclusion, because this is more of the space-time property than the plasma. And we expect that if your mismatch is more than 5%, then you have clear distinguishable between the Kerr and KRG black hole, or any other black hole which is away from the Kerr black hole. Okay, thank you.
Thank you, Akhil. Thank you so much for the talk. And we have about 5 minutes for questions.
Yeah.
Any question from the audience? Bożena, please.
Okay, I can start. I still worry about the precision of modeling the plasma around Sagittarius A star, because when you show the movie from Sagittarius A star, you see that the image changes. And if you look at the flux in millimeter band or mid-infrared, you see mostly flares. And this is not reproduced, I think, by the models, because magnetic field reconnection, etc., is not included. So maybe those processes, their complexity, will actually still mask the differences in GR or non-GR, even in the future. Can you comment on that?
Yeah, so of course there are, yes, I think. Yeah, so of course we know that the plasma physics, there's something missing in the plasma physics as well. We don't know yet whether what kind of modeling we can do to explain all of these constraints that we have for the Sagittarius A star. We are trying different models as well, like wind-fed model and other models to understand this. But one of the possibilities is, okay, we wanted to explore whether the first thing that we wanted to explore is what happens to these models when you go in a different theory. And to understand that, we don't actually have much resolution. Like you said, you have a flares, but flares is maybe not coming from the space-time properties, probably some because of the magnetic field around it. And we understand that this can happen for the MAT case very clearly. Although this doesn't tell that, okay, there when you go very close to the black hole, the alternative theories cannot produce that. So we're trying to understand what happens to all of these physics when. So first thing is like whether you can test it or not, and the second thing, if you can test it, what will be the differences when you move to the different space-time? So the simple question is, so we're trying to understand now what happens to the jet. So since we don't have any jet for Sagittarius A star, so whether we have some differences for different theories or not. Yeah.
Okay, thank
Yeah.
you.
Now, Mikołaj Korzyński from Zoom.
Okay, thank you very much. This was a very interesting talk. I have also a question regarding plasma, but this is more related to the way you perform ray tracing in your work. Do you somehow consider the influence of plasma on light propagation or the effects of birefringence, magnetic fields, or just propagation in plasma of electromagnetic waves? Or do you just solve null geodesic equation?
Yeah, in this case, we just solved null geodesic equation. We haven't considered any other electromagnetic waves or anything. It's just basically you have a plasma, you retrace your null geodesics, and you do the radiative transfer equations to solve the radiative transfer to solve basically the intensity of this plasma. So no other physics. It's simple the null geodesic calculations.
Thank you very much.
Yeah.
Okay. More questions, please.
Okay, I have a question about this space-time. What are the effects of the implementing this space-time, for example, during the black hole merger? Because potentially we can maybe find a constraint in the gravitational waves about these different models of GR.
Yes, so that's something is very interesting, but we don't know yet what will happen during the merger for this space-time. But we can do the approximate mapping into these KRG parameters for the merger time. I'm not sure if people have done it, but this is something I also plan to do, whether we can have an analytical form to perform some less expensive simulation with that. But I'm not sure what would be the effect.
Thank you.
Okay, and any more questions from Zoom or from the audience? Yes,
Can I just ask quickly? You showed there is a difference in jet strength when considering this slide. Have you analyzed what is the basic difference in how the Blandford-Naik mechanism would work, whether there is difference in the magnetic flux across the horizon or the area of the horizon, or something else is responsible for this?
Yes, so I think we looked into that, although we want to do more analysis on that, but for time being, we just calculated the flux at the horizon, and we see that it's for the KRG black hole, it kind of decreases also. But there's no systematic, because when you increase this frame dragging, so the black one is Kerr, and when you increase the frame dragging, then this blue one increases. But then if you introduce the maximum frame dragging effect, where your magnetic field gets more attached to this black hole, somehow the flux goes on decreasing. We still trying to understand why this happens, but probably it's happening because of not because of the frame dragging, but there's something else is going on. Yeah.
Thank you.
Mhm. Any other questions? Yeah, I cannot see. Well, I just have very simple question, but for me, this generalized solution should reproduce some features like the location of the horizon or the ergosphere of the black hole. So where it is for your KRZ metric? Where is the horizon and ergosphere?
So for this particular case, for all of these simulation, we fix the horizon for for what we have for Kerr case with spin 0.9375, which is like 1.334 Rg. So we fix the horizon for all of the simulations, for all of the KRG cases. Although you can always change the horizon as well, but we wanted to make it more consistent and doesn't have much degree of freedom. So we want to only see the effect of the frame dragging. So we fix that. For the ergo reason, I think I should have it here. Yeah, so for ergo reason, we see that from Kerr to this extremum KRG case, it actually goes, okay, this is GT5 by G55 at phi equal to 0. And we see it goes much more closer, but the frequency itself increases a lot. So I think but this also comes from the fact that you don't really change the A0 and A1 has this positive and negative sign, but overall frequency increases, but ergo reason decreases compared to the Kerr.
Okay, thank you for answer. Can't see any further discussion. So thank you for sharing your slides. And we are supposed to have a second talk, but is the speaker with us? Hello.
Hi, sorry, I had a little trouble joining, but I'm here now.
Okay, so good. Now we have the second seminar as announced, and let me introduce this a bit different topic, not about the black holes, but still about GRMHD simulations. So it's all in line with our topics. And let me just introduce the speaker of the talk. Is Jiao Desai, currently working as a postdoctoral fellow at the University of Greifswald in Germany, and he's a Humboldt fellow there. He graduated 2023 from Columbia University, doing research on neutrino-driven winds from magnetized proto-neutron stars. Prior to that, he visited the Perimeter Institute and Los Alamos National Lab, and he did graduate from University of California. So please go ahead with your talk about neutrino-driven winds.
Thank you. Okay, let me see. Can you all see?
Yes.
Okay. So I apologize if it's a bit, if it's a bit. I just submitted my paper a couple of days ago, and I just made this presentation. So let's see how it goes. Okay. So yeah, I'll focus mostly on the paper I just submitted, and that's about relativistic jets from millisecond proto-magnetars and how these can be central engines for gamma ray bursts. Let me just make this small. Okay. So just to get everyone on the same page, I'm sure most of you are familiar, but I'd like to start with what we actually observe, which are gamma ray bursts, right? So these are seconds long durations of gamma ray emission observables. We observed many of these by now. For example, here's one counts per second, and this is the one associated with the gravitational wave observation in 2017. And so they're thought to be powered by the dissipation of energy within a collimated relativistic jet. Here's a picture actually from our simulations of a close-up of the jet, the beginning of the jet. And the astrophysical sites are either central engines. So the central engines of these jets are either proto-magnetars, which are just strongly magnetized hot neutron stars. So it's hot because there's a brand newly formed neutron stars. And so they have high temperatures and they're emitting lots of neutrinos. Or they could be powered by black holes. But yeah, so the astrophysical sites are the remnants of these of compact object mergers or collapsed massive star cores, and they're often discovered along with other signals. So they're one of many multi-messenger observations. Other possible signals are neutrinos, although we haven't detected any concurrently with the GRBs. And then gravitational waves, for example, 2017 with the neutron star merger observation, the famous one. Cosmic rays are another possibility. And of course, transients across the electromagnetic spectrum from gamma rays to radio, which we did discover as well in 2017. And all these together can help us address big open questions like sites of our process element production. I'm not sure how familiar you guys are, but it's these are among the heaviest elements in the periodic table, and there are many uncertainties that go into producing these elements, from astrophysical to nuclear uncertainties. So that's what makes them very interesting to study. It's another component of my research that I'm also interested in, but I won't talk as much today about. And then also physics of neutrinos, there are a lot of uncertainties there. We can learn something about that. And also tests of general relativity, as you know, the central engines are neutron stars and black holes. So we can also learn something about, we can also test general GR in this way. So that's some reasons why GRBs may be of interest. And of course, the highlight again is the 2017 event. Yeah, so another thing I just want to clear up is that the central engine, and yes, again, it can be either a proto-magnetar or a black hole. If it's a proto-magnetar, the energy event has to come from its rotational energy somehow, the rotational energy of the neutron star. If it's a black hole, the idea is that it's powered by the accretion of material that, say, of the progenitor massive star, either from the core or from fallback from outer layers. And the jet operates via this Blandford-Zerniak mechanism. Thus far, actually, black holes have been favored as GRB central engines, but I'm focusing on proto-magnetars as a viable alternative. So these are some questions I aim to address. So the first one, again, I'm not really focusing on in this talk, but it is another focus for my research. And in this talk, I want to look at the properties of the central engine of these bursts and how they can actually power a jet, the properties of proto-magnetars in particular. So here are some open questions in general about these jets. How do they form in the first place? What are the ingredients? How do we get to the ingredients that are required in the first place? The appropriate magnetic field strengths, the rotation rates, the neutrino heating, and once the jet is formed, how do we connect? Once we get those ingredients, how do the outflows look like? How do we connect these outflows to the GRB observations? And from those, what can we say about the properties of the central engine, the spin, and the magnetic field? And then also so these are what makes these systems very difficult to study or to understand is that they take place over many different scales. So across very small scales, just the central engine itself, to like tens of thousands of kilometers, because the jet really goes this far away from the central engine before it starts radiating and forms the GRB that we actually see. And so there's a question of how do we convert the energy, which may be mostly a magnetic energy initially as the material is leaving the central engine. How does that convert into kinetic energy? How does material accelerate and match the high observed Lorentz factors that we do observe in these jets? So that's another question, but I also won't be focusing on that. So I'll be focusing on the orange, which is, again, how do we what are the outflow properties once we have a jet, once we have the ingredients required? So previous works have studied, and more recently, some very interesting ones, I think, on how do we form these proto-magnetar jets. They look at global, self-consistent global simulations of mergers, for example, or even core collapse, or even accretion-induced white dwarf collapse simulations, which I didn't write here, where they find that large-scale magnetic fields can in fact be generated and reach magnetizations of around 1 to 10 in the short time scale that they're able to simulate, which is maybe tens to hundreds max milliseconds. So maybe we can produce such large-scale magnetic fields required. But once you have, assuming you have these large-scale magnetic fields, what do the outflow properties look like? And there have been several simplifying toy models that have studied these, or some 2D simulations that have studied these by my former advisor, Brian Metzger, or another set of 2D simulations by Bucchi and Tini, and more recently by Prasanna. And then assuming you have these jets, people have taken some angular profiles and injected them onto larger scale simulations to look at how the material accelerates, as I alluded to before. But again, that's not the focus of my work. So this is a central question of my work. Can a proto-magnetar power a jet? So to answer this question, let me just briefly go through the actual formation. So it starts with a core collapse of a massive star. The outer layers can be ejected, and the core itself can collapse into a neutron star. And so this neutron star heats up, and many copious neutrinos can be emitted. And so this is essentially gravitational energy being released in the form of neutrino emission, about 10 to the 53 ergs of energy. And so three key ingredients determine these outflow properties: the net neutrino heating, the rotation rate of the neutron star, which is amplified from the core collapse to the formation of the neutron star from the angular momentum conservation. So you can have rapid rotation of this neutron star, and magnetic field strength and geometry. So this is also amplified from flux freezing, but can be further amplified by dynamos. So in my previous works, I looked at how these different ingredients affect the outflows separately. And so a bit about the neutrino heating. How it works basically is the neutrinos first diffuse out very slowly, but then reach this neutrino sphere from which they are emitted. But there are two dominant reactions that occur: these heating reactions and the cooling reactions, basically neutrino absorption and emission. And this is baryonic, so neutrons and protons emitting or absorbing neutrinos. So if you look at the heating and cooling reaction rates, it turns out that heating dominates between a layer between 15 to 50 kilometers. And so this is called the gain layer. The point is that outflows are material is heated and driven outwards. And this is what forms this so-called neutrino-driven wind, just from these reactions. And so the point is that neutrino heating can load these field lines, which may already exist, with baryonic matter. And so if you add on top of that rotation and magnetic field lines, they can sling fluid along open field lines. So if you have strong enough magnetic fields, then these field lines, you can imagine they would be rigid enough such that they can actually sling fluids and accelerate material so that it can reach high velocities. Since in this environment, ideal MHD is really a good approximation here. So matter is kind of trapped along these field lines. So it's really the open field lines from which there would be outflows that we're interested. So these outflows from these remnants of core collapse or mergers, which form similar remnants, they can evolve over the timescales of seconds. So here's just different properties as a function of time starting from core collapse. And these properties evolve over the timescales of seconds. But for our simulations, we aim to capture steady state outflow configurations at a given moment in time. And in our simulations, we simulate for about 100 milliseconds. So we capture a single state from this entire long-term evolution. And here's just some typical neutrino properties at a given moment of time, maybe 10 to the 51 ergs per second, isotropic equivalent neutrino luminosities, 10 to the 20 MeV neutrino energies, and the neutrino sphere of the neutron star might be at around 10 kilometers. And so the point is that we use general-relativistic magnetohydrodynamic simulations as toy models, complicated toy models, yes, but I think we argue that they are necessary to some extent to better understand these outflows. So we don't form these proto-magnetars self-consistently from core collapse simulations, but the key is that this is idealized controlled environment. And we want to map this parameter space of spin period of the neutron star versus the magnetic field strength from, say, 10 to the 13th Gauss to 10 to the 15th, some of the, maybe the strongest, most strongly magnetized typical magnetic fields that we would expect, maybe even more than this we may expect. And from maybe periods of 16 milliseconds to 1 millisecond. The breakup of neutron stars is around 1 millisecond on rotation rate. So this is the region that we're interested in. And so our aim is to capture these steady state alphas for given neutrino properties, magnetic field properties, and rotation rates. What does the wind look like? And just a shout out to my previous work, we looked again at the isolated effects of just rotation, just magnetic fields. So the advantage in this approach is it allows us to disentangle different mechanisms at play and really tease out the physics. And the results are also agnostic of the progenitor. So they can be applied to the results of a core collapse simulation or merger remnants or merger simulations without having to actually run these expensive simulations over and over again just for different configurations. And this is also helpful to compare to observations, which of course may be many and diverse, and they're not just going to be one set of parameters always. So just some details of our scheme. We use a GRMHD code. We evolved the magnetic field, and we have this hydro solver, and with various things to handle the highly magnetized environments that we're interested in. We use a nuclear tabulated equation of state and a one-moment scheme for the neutrino transport. This is how our grid looks like. It's a set of grids and with the finest grid inside, just capturing the neutron star with the radius of around 30 kilometers, 10 to 30 kilometers, depending on the model. And we evolved the neutrino mean energies and number densities, and we modeled the emission and absorption of neutrinos. And so we evolved this for around 50 to 100 milliseconds to capture this steady state. And we also use reflection symmetry. We don't expect we don't expect there to be asymmetries. We've also tested it. So how we initialize these models, we start with a temperature profile of around 20 MeV central temperature. And we determine the metric at the initial time step. We don't evolve it further. We don't need to either, because the mass outflow rate is very small compared to the mass of neutron stars, so we don't expect the metric to evolve anyways. And then if it's a rotating model, then we also initialize it as a rotating neutron star. This is just an example of a result. Here's electron fraction, here's rotation. This is a 2D cross-section of our rotating neutron star. And then we allow that to come to a steady state, and then we turn the magnetic field on, a dipole magnetic field. So here's an example of a low magnetic field strength and high magnetic field strength. So we thread a large scale dipole magnetic field from on the neutron star, and we run that again for another 50 milliseconds to achieve some kind of steady state. So I'll jump right into the results. So here are, for the same magnetic field strength across these three models, 3 different rotation rates. So here's 18 millisecond rotation rate, around 2 milliseconds to 1 millisecond. The top is density, and the bottom is net neutrino heating. So anywhere where it's like yellowish down here, there's net neutrino heating, and this is where matter is large outflows are being driven. And so here you can see that from as the rotation rate increases, you get a large centrifugal boost because of the high rotation rate in the equatorial region. And so you get high density outflows in the equator, high m dot as well, as opposed to the polar region, in particular for the rapidly rotating model, compared to the slower rotating models. And then on the top, I show the same thing, same models, but on the top I show here now velocity, and on the bottom I show magnetization. So that's the magnetic energy divided by the rest mass energy density, rest mass energy. Magnetic divided by rest mass energy. And so for the 18 millisecond model, we don't see extremely high velocities, maybe about 0.1 C maximum. Here, now we see this angular gradient and moderately maybe trans-relativistic velocity is around 0.5 C. And for the rapidly rotating one, now we see sort of these collimated outflows, and we see sort of the same pattern, except in the velocity structure here, except much more collimated. All directed in the polar direction, and reaching velocities around 0.7 to 0.8 C in these wings. And for magnetization here, for around 18 millisecond period, we see not very magnetized at all, to magnetization greater than 1, maybe around 1 to 10. And then here we see highly magnetized outflows from 10 to 100, maybe even more, some clumps of more than 100 magnetization, which is quite a lot for these models, and compared to what is typically expected, I guess.
May I interrupt, because we just have 5 minutes left, so maybe you could just come to some conclusions and then we ask questions.
Yeah. I have conclusions here. Like 2 slides left.
Okay.
So I don't have that much left. So okay, I already discussed this. Here's just a video of this highly magnetized outflows, and the point is that we see this distribution in magnetization. And so, for example, in fluid with magnetization greater than 20, we see it contains a total power of around 10 to the 50 ergs per second isotropic equivalent luminosity. And we plotted the total energy, the total kinetic energy of our outflows versus the total electromagnetic energy of our outflows, and compared this to the observations of gamma ray bursts and their associated kilonova energies. And we find that for our most rapidly rotating models, it sits sort of in the middle of the observations. So that's somewhat promising. And then I'll just come to my conclusions here. So I guess one of the points is that we see continuous transition across all of our models from low to high magnetization in our outflow properties, and also from low to high rotation rates. And then for our most rapidly rotating model, we have massive equatorial outflows, which help to naturally collimate the jet, which has been an issue for previous works. But this also enables efficient conversion from magnetic to, because it's collimated, it enables this efficient conversion from magnetic to kinetic energy at large distances, which is helpful to explain high Lorentz factors that we observe in the jets from GRBs. And so from our models, I think we've revealed multidimensional effects that are not captured by these simpler models, particularly in the polar outflows. We achieved sigma of around 100 to 200 for some fluid, and this is really applicable to a wide range of energetic explosive events. So accretion-induced white dwarf collapse systems as well, because you can form a similar remnant there, or remnants from mergers, and again remnants from core collapse. So yeah, that's it.
That's it. Thank you so much for the talk, and yeah, we have time for a couple questions, of course. Bożena, please.
My first question is about this jet acceleration, because normally I think in your model you say you can have a large fraction of C, like 0.7, 0.8, something like that. But for gamma ray bursts, you need Doppler factor 100 or few hundreds. So would you say that the jet is accelerated at larger distance than it's covered by your simulations, or you would need another extra mechanism which is not included?
Yeah, I think you have it right. So at these distances, we don't expect to get to Lorentz factors of 100 just within our simulation domain of around 1,000 kilometers. But the point is that the kind of potential energy is there, so that the energy is stored in the magnetic energy, and in that magnetic energy we have magnetization, which is approximately this maximum achievable Lorentz factor of around 100, of around 10 to 100, depending on how much power you care about, and so it has that potential to accelerate later at larger distances, but within our domain we don't see those accelerations, nor do we necessarily expect to. Does that answer your question?
I guess, yeah. Other questions on Zoom from the audience? Yeah, so I have a question about other electromagnetic counterparts. Apart from the gamma rays, we observe these lower energies and the kilonova you mentioned. So how in this model will reproduce observations of the kilonova and various colors that we have a handful of data for?
Sorry, what was the first part?
Kilonova, basically the electromagnetic counterparts at lower energies. Yeah. How you account for that?
How do we so I guess I should say that we're not, so in the merger context, we don't include, for example, like a disk that is likely to account for a significant fraction of the energy budget. So like the outflows from disk winds, for example. So in that sense, our models are kind of like a lower limit for the total kinetic energy that one might expect for kilonovae. But yeah, so I guess our models are limited in the sense that we're just looking at the outflows from the engine itself. But I'm not sure if I answered your question fully, though.
Well, maybe a follow-up question also, because what I understood from the presentation, you aim to explain various GRBs by the magnetar scenario, so both long and short GRBs, and also the kilonova are associated actually with both types. So how this universal scheme is possible?
How is it possible? So we also don't really track the evolution on long over long timescales. We only model steady state these steady state winds, so around 100 milliseconds, and these GRBs can last for several seconds to maybe several seconds, right? So that would require like more long-term simulations, but what was your question again? I think.
Well, to have a long GRB, you would need to have this magnetar pin down period quite long, right? So I guess your scenario is applicable for long GRBs as well.
Yeah.
Right?
Yes. So the thing is that with the proto-magnetar jets, over time, the neutrino luminosities, which scale with the mass loss rate, the neutrino luminosities would go down because the neutron star is cooling, so less neutrinos, so less mass loss rate. And so the magnetization would only increase. And so as time goes on, we would go from a model that maybe looks something like this. You can see my screen still? That looks like this 1 millisecond. These 1 millisecond winds to the slower rotating ones, and with even higher magnetization than even what the models that we have here. because you'd have a lot less mass, for example. So you see the magnetization cover a larger range of angles as well. So in that sense, our simulations covered the early times, actually. Our models are really for the early times where you have high neutrino where you expect high neutrino luminosities, because that's the neutrino luminosities that we are using here. And I think another interesting thing is that we can explain even the prompt GRBs, because for example, the one that was detected after GW17 or 17 after about 2.7 seconds. And so the problem, the challenge that a proto-magnetar engine faced initially is that, well, you have high mass loss rate. So how do you achieve significant magnetization at such an early time? Because the field lines would be heavily loaded with mass, and so it's hard to achieve this high magnetization. But we're showing here that you can actually, in the polar direction at least, even if not in the equatorial region, in the polar direction, you can still achieve this high magnetization. And with time, this magnetization would really only increase due to the decreasing neutrino luminosities. Does that answer your question?
Sort of, yes.
I have also one
Bożena.
more question or comment, because you didn't speak much about this proto-magnetar state. That if this proto-magnetar state is a very massive star, like above 2 solar masses differentially rotating, then it can change the state, right, during the evolution. So then you can have an evolving engine, right? Because when this differential rotation is going down, then a lot of things changes. And maybe this will contribute also to the long duration. But I don't know what are the time scales for the decay of differentially rotating neutron star.
So yeah, the engine properties can certainly change, will change in time. I think the differential rotation will also be there in the beginning, but then I think that is expected to die down pretty quickly, maybe within hundreds of milliseconds, maybe.
Yeah. I don't know.
And eventually, so we in our simulations we just look at we assume rigid body rotation, so we don't assume differential rotation. But yeah, I think that it's only differentially rotating for a limited amount of time. It's not going to be differentially rotating for seconds, for example. I think within a second it's
the evolving engine, right?
Yeah, the engine can certainly evolve. So I think that's another advantage of our models, that we can sort of map out different points in time of the outflows, not just after 1 second, but maybe after 2 seconds or 3 seconds, by changing the central temperature that we initialize the neutron star with, or by changing the magnetic field strength, for example. So we're able to do that with our models, although the question of numerical stability is a different thing. But
thank you. That was fine. I guess we are running out of time, but if anybody has some urgent question, you're welcome. If not, then we conclude the seminar, and that's all for the open session.
Okay.
Thank you for the talk.
Thank you.